Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson number 1 on circle terminology. Now Unit 9 is devoted entirely to the geometry of circles. And I'm not talking about the area and the circumference of circles. We're going to be discussing those in Unit 10 when we look at measurement and modeling within geometry. I'm talking about all sorts of properties of circles that don't have to do with the space inside them or the length around them. And it's really impressive how many properties circles have. So let's get right into it today by learning some of the essential terminology we need to know. Now, we've got the circle definition and basic terminology. Most of the shapes that we've worked with in this course have been polygons, which have straight line segments as edges. A very important shape that is not a polygon is a circle. And it's important to know its definition. Really important to know its definition. So let's take a look. The circle. A circle is the collection of all points that lie a fixed distance away from a given point. The given point is called the center of the circle. Now, this is absolutely critical because you've been seeing circles probably since before you could even talk, right? In your fundamental little picture books that your parents were probably showing you when you were very, very young, there were circles and they likely pointed at them and said, that's a circle, right? But what truly defines a circle is the collection of all points that lie a fixed distance, a given distance, away from some other point, which we call the center of the circle. Now, there are many important pieces of terminology associated with circles, some of which you should already know from previous courses. So let's take a look at some basic terminology. All right, number 1, a radius is any line segment drawn from the center of the circle to a point on the circle. 2, a chord is any line segment whose endpoints both lie on the circle. And 3, a diameter is any chord that passes through the center of the circle. All right, awesome. Now, of these 3 pieces of terminology, you should know both radius and diameter, but chord might be a little bit new. But again, a chord is an easy idea. You know, you put one point on a circle, you put another point on the circle, you draw a line segment in between them, and that's a chord. All right, that's all a chord is. But chords are very important in circle geometry. So let's take a look at exercise number 1. Circles are often named using their center. In the following diagram of circle A, the points B, C, and D lie in the circle and are marked. Points A, C, and D are collinear. Letter A. List 3 segments that represent radii of this circle. All right, excellent. Now remember, a radius is any line segment drawn from the center of the circle to a point on the circle. So pause the video now and list 3 line segments that represent radii of this circle. Well, simple enough, right? Here's our center at A. Here's a point on the circle B. Since there's a segment drawn between the two, AB is a radii, or a radius. Sorry, AD is a radius and AC is a radius. So there are our 3 radii on this circle that are currently drawn. Every circle has an infinite number of radii that can be drawn. In this particular diagram, we have 3 of them. All right, let's take a look at letter B. Name the one segment that is a diameter of this circle. What is the relationship between its length and the length of any radii? Awesome. Okay, there is one chord, one segment here that's a diameter. And remember, a diameter is just a special case of a chord, right? It is a chord, right? So it's a segment that's got its endpoints both on the circle, but that pass through the center. Go ahead and write down the name of the diameter and then explain to me what the relationship is between its length and the length of any of the radii. All right, because we're told that points A, C, and D are collinear, and CD is definitely a chord, then CD must also be a diameter because it passes through the center of the circle. All right. Now the other thing though that we can note, right, is that CD is obviously CA plus AD, right? And because CA or CD is equal to CA plus AD, and both of these are radii, right, then obviously any diameter's length is going to be twice the length of any radius. All right, so any diameter length will be equal to twice, or let me use the word, twice, there's my red, the length of any radius. Let's maybe make those a little bit better. There we go. All right, and that's certainly something that you've seen plenty of times before. Let's keep going. Letter C. List all chords of the circle that are currently drawn. All right, great. Again, look at the definition of a chord and go ahead and list the two segments here that are chords. Okay, well again, a chord is any line segment whose endpoints both lie on the circle. And remember, the circle is the collection of these points. It's not the entire shape, right? It's just the collection of these points. Therefore, we've got one chord that goes from B to D, so segment BD is a chord, and that diameter that we just looked at, CD, is also a chord. So BD is a chord, and CD is a chord. All right, final problem in exercise number 1, letter D. Explain why angle ADB must be congruent to angle ABD. All right, I'd like you to take a moment, locate these two angles on the diagram, and see if you can explain to me why those two angles must be congruent. All right, well, let's take a look at them, right? Angle ADB is right here, and angle ABD is right there. Let me actually mark them as congruent. That's what we're trying to explain, but that might help us understand why. Now, this is actually a very, very important problem for what we're going to be doing in the future in this unit, okay? Now, why must those two angles be congruent? Well, what do we know, right, in this diagram? One thing that we know is that AD and AB are both radii, right? So AD and AB are both radii, but by the very definition of a circle, that means that AD must be congruent to AB. And this is what it's all about with circles, right? Every property that a circle has comes from the fact that all of its radii are the same length. Every property. And this is one right away, right? So AD and AB are both radii, so AD and AB are congruent, right? This means, of course, that we've got an isosceles triangles, right? This means triangle ADB is isosceles, which means its base angles are congruent, right? This is congruent to this, which means this angle is congruent to that. And we're going to see isosceles triangles pop up a lot in geometry specifically because of this property. Okay, let's keep going and learn more terminology associated with circles. But first, let's do exercise number 2. In circle M, point A is located on the circle such that AM equals 2x plus 7. If the diameter of circle M is 74 inches long, then what is the value of x? Show how you found your answer. All right, well, I'd like you to pause the video right now and play around a little bit with this problem and see if you can figure out what the value of x is. All right, well, I'm going to draw a nice diagram. Okay, it doesn't have to be much. Now, one thing that I know right away is because it's called circle M, what that tells me is that point M is in the center of the circle. Okay, it tells me that point A is located on the circle and that AM, that segment, has a length given by the algebraic expression 2x plus 7. We know that the diameter of the circle, right, this length, is going to be 74. And I want to solve for x. There's a couple different ways I could do it. I could say that that's 2x plus 7 and that's 2x plus 7, and I could add them together and set it equal to 74. Or I could figure out what the radius is, right? The radius is 74 divided by 2, which is going to be 37 inches. All right. And once I have that 37 inches, that's the length of AM. Maybe I'll write that down formally here. And so now I can say that 2x plus 7 is equal to 37. Easy enough at this point to solve a nice two-step equation from 7th grade, and we get x equals 15. All right, that's it, right? But it does incorporate some nice things, right? The relationship between the diameter and the radius of a circle, the fact that we name circles using their center point, the fact that, if we've got a point located on the circle, then the segment that connects the center to that point is a radius, etc. All right, let's take a look at some more. Now, arcs along circles, very important. We've talked about arcs throughout the course. We've used them extensively when we've made constructions, but now they're going to become really important in this unit. When 2 points lie in a circle, the portion of the circle between the 2 points is known as an arc of the circle. Arcs are named like segments using their endpoints, but unlike segments, there is one complication. Let's take a look at that. Exercise number 3. In the diagram of circle O below, points A, B, C, and D all lie on the circle with diameter BD. Letter A. Name the minor and the major arcs that have A, B as their endpoints. All right, so let's talk about this complication. All right, if I take a circle, which is like a line that's kind of been bent around itself and goes on forever that way, I can locate 2 points. Let's say that we're thinking about just the points A and B. Now there's an arc of the circle that lies between AB in this direction, and there's an arc of a circle that lies between AB in this direction. A minor arc is an arc that takes up less than half of the circle, and a major arc is an arc that takes up more than half of the circle. If the arc takes up exactly half of the circle, we literally call it a semicircle. So minor arcs are very easy to name. All you do is write down their 2 endpoints just like you would with a segment, and then you put an arc symbol above it. Real simple, right? So minor arc AB. Now major arcs, because they extend more than half the circle, we will still name them with their endpoints, but we have to have 1 point, at least 1 point in between. So in between A, B in this direction are both points D and C. So I could call this arc many different things. One thing I could call it would be arc ADB, or I could call it arc ACB, or I could get crazy and I could actually put all the letters ADCB, right, which would be just getting a little bit out of hand. Any of these are okay, all right? And let's give a nod to this. Of course, the minor arc could have been arc BA, or this could have been arc BDA. All right, so it doesn't really matter which letter comes first and which letter comes last, but the important things about minor and major arcs is that whole less than half the circle, more than half the circle. Minor arcs are less than half the circle, major arcs are more. All right, simple enough. Now let's see if you kind of understand that idea in letter B. Name the minor and major arcs that have A and C as their endpoints. Okay, go for it. All right, well, for our minor arc, we could call that either AC or we could call it CA. All right, either one of those would be fine. The major arc, on the other hand, right, that one I can either call ABC or CBA. And again, it really just doesn't matter, but we do have to use 3 letters to indicate that it is more than half of a circle. All right, that's it. Now, arcs are extremely, extremely important in this unit. So you have to feel comfortable with how you name them. Now, before we talk very much more about arcs, let's talk about what are called central angles. Arcs will play a very important role in circle geometry. Although their physical length can and will be determined, their measure will represent how many degrees around the circle, around a complete rotation they represent. To define this, we must first define a central angle of a circle. So again, before we move on, when we measure arcs, we're going to measure them in terms of degrees. A 90-degree arc, a 120-degree arc, a 270-degree arc, okay? But how do we measure the degree measure of an arc? Well, we get into that by using central angles. So let's take a look at what a central angle is. A central angle of a circle is any angle that has the center of the circle as its vertex. We typically name the angle using 2 points that lie on the circle and the circle's center. All right, so very easy idea. Now there's going to be lots of angles associated with circle work. All right, but the one that we're looking at right now is called a central angle. And all that is an angle that as its vertex is the center of the circle. So let's just make sure we can identify a central angle in exercise number 4. Let's take a look. Given circle B shown below with points A, C, D, and E lying on the circle, which of the following angles represents a central angle of this circle? Now, there's numerous central angles in this particular diagram, but only one of the 4 choices actually represents a central angle. See if you can figure out which. All right, well, a central angle has to have the center as its vertex, right? Got to have this as its vertex, and the only one of these angles that does that is angle CBA, right? That's this particular angle. All right. All the other angles in this particular diagram have points on the circle as their vertices, and those aren't central angles. They are special types of angles. We'll get into them in the next lesson, but for right now, we only want to be thinking about central angles. Okay, let's keep going. Now, the measure of an arc. We can now define the measure of an arc as equal to the degree measure of the central angle that intercepts it. Okay, and again, this is not complicated. The idea of the measure of an arc is real simple. If we took any circle, right, and we divided it up, the circle into 360 equal partitions, right, and we counted how many of them were between points, right, or that lie along a particular arc, that is the degree measure of the arc, right? It's like putting a really big protractor, a 360 degree protractor around our circle. That's all it is, okay? But let's take a look at exercise number 5 just to play around a little bit with the measure of arcs. Exercise 5. In circle M, points A, B, and C lie on the circle forming the central angles shown. Find each of the following. Letter A, the measure of arc AB. All right, well, this is as simple as it gets. The measure of arc AB, that's a minor arc, right, that goes from A to B or B to A, depending on how you want to look at it, has the same measure as the central angle that intercepts it. So the measure of arc AB is equal to 115 degrees. All right, just by definition of what the measure of an arc is. Now let's take a look at the measure of arc BC. Well, that's exactly the same, right? Because the measure of arc BC is just going to be defined by the central angle that intercepts it, and that is 90 degrees because we've got that 90-degree angle. All right, so those two are literally the very definition of central angles compared to arc measures. Now let's take a look at letter C. The measure of arc ACB. All right, now this finally we get ourselves a major arc. And the measure of arc ACB, right, is going to be the degree measure of that. And you can almost think about this as how much would I have to rotate point A to get it to point B if I'm going counterclockwise, all right? Now, there's a few different ways to do that, okay? But probably the easiest way is noting that the entire arc measure around a circle will always be 360 degrees. So the measure of arc ACB is probably most easily determined by doing 360 degrees minus 115 degrees, right? So I can really think of this as 360 degrees minus the measure of arc AB. And that will always, by the way, be the relationship between the measure of a major arc and its corresponding minor arc. They will always add up to 360 degrees, so if I want to find one and I have the other, I can just subtract it from 360. So in this case, I'll just do 360 degrees minus 115 degrees. This is where all I want is just a nice, simple scientific calculator to help me do the subtraction quickly. And I find that that's 245 degrees. All right. And finally, we want to find, not finally, we've got two more left. I want to find the measure of arc AC and the measure of arc CAB. Here's what I'd like you to do. I'd like you to pause the video now and see if you can work out what both of those arc measures are. All right, so for AC, we've got lots of choices. One choice would be to do 360, right? So AC is this one right here. One choice would be to do 360 minus the 115 plus the 90. The other thing that we could do is take the one that we just had, the measure of arc ACB, and just subtract off the 90, right? Because that 90, once we take it away, just becomes the measure of arc AC, which is, I think, what I'm going to do. All right, I think I'm just going to do 245 degrees minus 90 degrees, which should be 155 degrees. Again, you would get that same answer either way. And finally, our last one, let me get rid of all of this so that I can highlight this. The measure of arc CAB, again, this is now a major arc, right? That one. Well, that one we can actually do as a sum, right? So for this one, I can, well, or I can do it as a subtraction again. So for CAB, I could either take the answer I just got for AC and add it to 115, that would work just fine, or I could take 360 and subtract off the 90. And I think that's what I'm going to go with. So arc CAB is 360 degrees minus 90 degrees, which is 270 degrees. So there's lots of different ways, especially once we know some of the arcs, of finding all the rest of them, all right? A very, very important relationship is this relationship between a major arc and a minor arc. We see it in this problem. We also see it in this problem. But arcs, just like any other angle, will add, right? So we can add arcs together to get larger arcs. We can subtract them if one arc is part of another one, etc. And again, very, very simple. Think about this as being a clock, right? And having it divided up into 360 equal parts. Very important. All right, let's summarize. Now, this is going to be a lengthy unit, to put it mildly, right? And all of this terminology that we're going to learn at the beginning and all the relationships we're going to see is very important. But make no doubt about it, the most important thing that we saw today was literally the definition of a circle, right? This idea that it's a collection of points that are all the same distance away from some central point, right? That gives rise to the idea of radii of a circle and the idea that all radii of a given circle are the same length. That is going to give rise to basically every other thing that shows up in this unit. All right? But we're going to see more of that consequence in the next lesson when we start talking about what are known as inscribed angles. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.